Okay, thank you very much for the introduction. So can you hear me clearly? Okay. So thanks a lot for letting me join this workshop. It's very interesting topic. So actually, I'm trying to understand the meaning of engineering significant difference. So my topic is about approximate computing, and also I will discuss the security of the approximate computing itself. Okay. So my talk will cover this. So first is the motivation of why we need the approximate computing. And as the main study is on the computer arithmetic, so I will talk about approximate multipliers. And then I will talk about how this kind of approximate multiplier can be used in the AI algorithms, like the deep neural network and the code design methodology. And then in the last, I will talk about the security issues of the approximate computing itself. So why we need the approximate computing? So as we know that as the technology node is going down below 7 nanometer, so it is very difficult to further improve the performance and the same power level. So the power has become the main bottleneck for the computing systems. So we believe that today's hardware layers are somewhat over-engineered, okay, related to what is needed. And we are lucky to have a number of modern applications that is error tolerant. So for example, the artificial intelligence, digital signal processing, and also the communication systems. So for example, in the AI applications, actually, for for the model-based supervised learning, we don't have the golden answer, okay? And also, for some cases, the highest scores wins. That means the winner takes all. And also, we have a number of nonlinear operations like the thresholding and also the activation functions. So for all these kind of computations, actually, we don't need the exact computing. So that's why we can apply this approximate designs into these applications. So the idea of approximate computing is to further introduce the accuracy or the computation accuracy as the third dimension for the design space. So the conventionally we care about the performance and the power of the area. It's a two-dimensional design space. And now we further introduce a third dimension that is computation accuracy. So now it's three-dimension space. So actually, we don't want to introduce a large errors. Actually, we just want slightly allow some acceptable errors. But at the same time, we can reduce the energy significantly. So this is important. So to achieve this target, the error analysis and accuracy control is very important. So as shown in these figures, so okay, so from the beginning, the S0 is actually the exact design. So what we would like to achieve is that we can slightly decrease the accuracy of the computation results. However, we can further improve the speed performance and also reduce the power consumption. However, we cannot go beyond the S2, the point S2, because it's the results will be unacceptable. So the preferred design, okay, it should be fair in this reasonable range of the accuracy. So to perform the error analysis, that's a number of error metrics has been proposed for the arithmetic circuits, like the approximate adders and the multipliers. So which are defined based on the error distance. So actually they are the Hamming distance between the exact result and also the approximate results. So here we show two examples from the industry. Okay, so first is from the IBM. They have proposed a rapid multi-top accelerator for the AI algorithms using the approximate computing. So here it shows the accelerator cores. As we can see that it has a number of the process element. So in this process element is consumes around 80% of the whole power consumption of this chip. And in this approximate processing elements, there are several arithmetic units. So it can support FP16 and the integer 2 and also the binary. So they can change to different accuracy for different applications. And also here show the chip layout. And also they have some other nonlinear functions. So this chip is also a prototype chip. It's not used in the real product. However, the second example is from the Samsung. It's a PAM4 4-lane transceivers. So as I know, I think this one has already been used in some real chips. So in this transceivers, okay, as we know that it has the DSP part. Okay, in this DSP part, there's some equalization and also the FR filters. So in this kind of DSP processing, they have replaced the exact multipliers using this kind of approximate multiplier. And for the, okay, so they have shown that by using this kind of approximate multiplier, they can reduce the power up to 40%. And however, the results didn't affect. This means that the accuracy is more or less the same. Okay, so that's the motivation of why we can why we use approximate computing and how it can be used in the real chips. And the second part, I will talk about the main study on the approximate arithmetic, especially the multipliers. As we know, that's the multiplication is the most most used operations in the AI algorithms and also in the DSP systems. So for the approximate multipliers, we can mainly divide it into the 3 kind of designs. So the first one is we can approximate the operand first. That means we can use a different, we can change the original A and B to our approximate one, and then we can do the multiplication. And the second and the third approach are just based on the exact design, and then we can do the approximate partial product generation and also the reduction. So in the first approach, that we can change the original operands. So for example, for this dynamic range unbiased multiplier, which named as drum. So for the operands, we can first find the leading one. So that's we use the leading one detection to find the first one. And then we can keep the following k bits. And then we can truncate it, the least significant bits. And in this way, we can just use a smaller multiplier to perform a larger size multiplication. So here we'll show an example. So for example, this A cross B, that we can find the leading one first, and then we can have 6 base for this operands, and then we can perform this multiplication, and it can save the power in the different application like the image filtering or the JPEG compression, that we can achieve a significant power saving. And another way to do the approximate operand is to use the logarithm multiplier, so which is change the A cross B to log A plus log B. So in this way, we can just use an adder rather than use the multiplication. However, we also need to do the leading one detection first, and then do the logarithm converters. Then we can use the adder and do the anti-logarithm make converter. And also we can do some further optimization to have this dynamic range. So we can just do some dynamic truncation to get a better design. And also after the addition, we can do some error compensation for better accuracies. So we have to do some comparison between this drum multiplier and also the logarithm multipliers. So as we can see that under the similar error, or under the similar accuracy, that actually the logarithm multipliers has the better power delay product. So generally, this kind of multipliers, they have lower accuracy, but they have also very low power. The second design is based on the approximate partial product generation. So the first one is under designed multiplier. So for example, the 2x2 UDM, we can just change one entry in the truth table of this multiplier to get a simplified design. So we can use this 2x2 multiplier to get 4x4 or 8x8, some larger size designs. Okay, so here we show the one used in the Samsung transceivers. So in their design, they so what they do is when they do the partial product reduction, rather than use a compressor or the exact half adders, they just use some OR gate or the half adders or approximate 4 adders for this kind of partial product reduction. The reason why they can use this is because they have do some analysis, and they found that when all the partial products are zero, the probability is very high, and when more than one, more than one is more than one is partial product is one, its probability is very low. So based on these results, they can use just a very simple OR gate or some approximate 4 adders. So here they show that the power can be saved by up to around 40%, and also the area can be reduced by over 30%. And also for the CD recover the CDR jitter tolerance, that we can see the right line is with the conventional exact multiplier, and the green one is using approximate multiplier. We can see it's more or less the same. So it does not affect the results of this jitter tolerant results. And also our group also proposes some approximate design by observing the probabilities of the partial products that we can. So the first step is that we rewrite this partial product by using the EKL and FKL, and we find that the F13 and F02 has a high probability of being 0. So we can combine this F and CD to one partial product, and then we can use an OR gate to compress this F30 and F21 together. So in this way, we can get a more efficient design for the multipliers. And also we make this kind of this design as an open source library. So if you feel interested, you can download and perform some simulation by yourself. So the third part is that we can use this kind of approximate multiplier in the deep neural networks. So as we know that the deep neural network has some error tolerance. However, if we directly apply this approximate multiplier in this neural network, actually it does not work because it has a convergence problem in the retraining stage. Because this will have some accumulated errors. So we have proposed an incremental network approximate algorithm, and we can have the energy reduction by up to from 30% to 80%, and also the accurate loss is below 2%. So the idea is here. So as we know, there's a lot of multiplication in the weight during the weight multiplication. So what we do is we just divided this all weight into, for example, 4 groups. Okay, so in the first step, we just replace one group of these multipliers with approximate designs, and then we do the retraining, and then we replace the second group with the approximate designs. So one by one we do it, and after the 4 steps, we can have the one all the multipliers are become the approximate designs. However, the accuracy is still the very high. I mean, the accuracy is still very high. As we can see in this, from the simple network to somewhat more complex network, from the MMP to ResNet 18, that's all this results are the accuracy loss are less than 2%, and we have up to 24% of the power reduction. Okay, so as the last part, I will discuss some security issues in the approximate computing itself. So as we know in the hardware design, we have some threats from the hardware trojans. So we have studied two kinds of trojans in the approximate circuits. So one is a functional destructive trojan. For example, if we insert this kind of trojan into adders, so for example, you can add it into the 4 bits, so Y0 to Y3, okay. So for example, if we insert this trojan to the Y1, that means in the second 4 adders. So actually you find that the error is even smaller than when we insert this trojans to the other sum bits. So which means it is very difficult to add this functional destructive trojans, because it will not affect the results, as the least significant bit is not very important in this approximate adders. However, this is opposite in the information leakage trojans. So for example, this trojan is inserted to try to reveal the key in this XOR gate. As we can see in the result, that they almost have the same error characteristics. So this means that you can so this can be very difficult to find this trojan, but it can still reveal some important informations. So this is only some very preliminary results from our study on this topic. And we also organized a special issue on the approximate computing in the proceeding of the IEEE. So if you feel interested in this topic, I think you can read the papers from this special issues. It can give you a full picture of this topic. Okay, thank you.